Hey guys, so today we're going to look at the acid-base properties of salt solutions. Before we just assumed that when acids and bases react, they form neutral solutions. But today we're going to see if that's actually true. The picture below shows the salt of copper 2 sulfate. Remember that a salt is any ionic compound, and an ionic compound consists of a lattice of alternating cations and anions. What we know already is that acids and bases react to produce a salt and water. Those salts, when they're dissolved in water, will dissociate into cations and anions. And again, previously we assumed that that would result in a neutral solution. But if we take a closer look, let's see if the cation or the anion can go on to react with water so that the resulting solution could end up either being neutral or acidic or basic. How could it be acidic or basic? Well, if the anion or the cation goes on to react with water in a hydrolysis reaction, then either a hydroxide or a hydronium ion will be produced. This will result in excess hydroxide or hydronium being added to the water equilibrium and results in either a basic or acidic solution. So let's look at the first example, salts that form neutral solutions. If we react a strong acid and a strong base together, we're going to end up getting something like sodium chloride. That sodium chloride will go on to dissociate into sodium ions and chloride ions. Neither of these ions has any tendency to hydrolyze or react with water. Sodium is a group 1 ion. It's incredibly stable. It has no desire to react any further, so there's no hydrolysis reaction. Looking at chloride and remembering what we learned about Bronsted-Lowry acids and bases, chloride is actually the conjugate base of the strong acid hydrochloric acid. Because it's the conjugate base of a strong acid, that makes it a very weak base, so it will not hydrolyze. If you look at the chart, it shows some other examples of cations and anions that will not further hydrolyze, and therefore these ones will result in the production of a neutral salt. What about salts that form acidic solutions? These are formed when you react a strong acid and a weak base. Now, often students make the mistake of saying, oh, okay, it's going to produce an acidic salt because we started with a strong acid. They couldn't be further from the truth. So let's take a look at the salt that's produced from this. Hydrochloric acid reacts with ammonia. The salt produced is ammonium chloride. Ammonium chloride will dissociate into ammonium and chloride. The ammonium is the conjugate acid of a weak base. That makes it a very strong acid. So because it's a strong acid, it will hydrolyze with water, and you can see the hydrolysis reaction at the bottom. When it reacts with water, it produces hydronium, and that excess hydronium is going to be added to the water equilibrium and making it acidic. The chloride ion is exactly what we had in the previous example. Recalling that it's the conjugate base of a strong acid, it's very weak, and so it won't hydrolyze. So since we only have one ion hydrolyzing, and it's an extra source of hydronium ions to the water equilibrium will have an excess of hydronium, resulting in a pH less than 7. Take a look at some other ions that will also result in acidic solutions. You might not have thought of aluminum ions or iron ions as being acids. However, an acid can be defined in several ways. Remember, originally we thought it had to contain hydrogen. Then we changed it to be any substance that could donate a hydrogen. If you look at the reaction at the bottom of the screen, you'll see that the hydrated aluminum ion can react with water to produce a hydronium ion and a complex ion. So since it has the ability to produce a hydronium ion, it acts as an acid. So again, because we've opened up the definitions of acids and bases, we can now consider aluminum ions and iron 3 plus ions to behave like weak acids. And if you don't believe me, you can actually look up the table of Ka values and you'll see that aluminum is listed there as well as iron. What about salts that form basic solutions? These are the product of weak acid, strong base reactions. Again, I want to point out to you, a lot of students think, okay, this is going to form a basic solution because I'm reacting a weak acid with a strong base. And they think there's leftover base. That is incorrect. For instance, if this is a neutralization reaction, all the acid and all the base is consumed. So all we're left with is water and the salt. Since we know water is neutral, the pH of the resulting solution is going to be affected only by the salt. Let's look at the cation and the anion that comes from the salt. Sodium acetate is the salt. The sodium ion, well, that's the cation we looked in the previous slides. Again, it's completely stable, has no tendency to react, so will not hydrolyze. The acetate ion, that is the conjugate base of the weak acid acetic acid. Because it's the conjugate base of a weak acid, it's a much stronger base than water. That means it's able to hydrolyze with water. And so if you look at the equilibrium reaction at the bottom, or the hydrolysis reaction of the acetate ion, you can see that it's reacting with water to produce hydroxide. So the hydrolysis reaction is the source of extra hydroxide ions that are going to be added to the water equilibrium. And because we've got extra hydroxide ions, the resulting solution is basic and we've got a pH greater than 7. Here's some other ions that are also the conjugate bases of weak acids. So they will hydrolyze and they will produce basic solutions. The last scenario is that we can have salts that have both a cation and an anion that are capable of hydrolyzing. So then if we have both occurring, how do we know whether it's going to be acidic, basic, or neutral? The answer is to look at all the equilibrium constants. If the Ka and the Kb are equal, that means the acid and base strengths are equal, and so that means we'll have an equal amount of hydronium and hydroxide, and so there'll be no net effect to the pH of the solution. It'll still be neutral. However, if the Ka is greater than the Kb, then the salt will result in an acidic solution. If the Ka is less than the Kb, then the salt will be a basic solution. So that's the qualitative aspect. Let's look at the quantitative aspect. Here's an example of a problem you would need to solve. Predicting whether a 0.2 molar solution of sodium cyanide would be acidic, basic, or neutral. We can discuss it qualitatively. The salt dissociates into sodium ions and cyanide ions. Sodium ions do not hydrolyze. Cyanide ions, that's the conjugate base of a weak acid. That means it will be a stronger base than water. That means it will hydrolyze to produce hydroxide ions. You can see in the box there that the cyanide ions go on to react with water to produce cyanic acid and hydroxide. Plugging into the ice table, the initial concentration of the cyanide ion would be 0.2, simply because it's present in equimolar amounts to the sodium cyanide. So we've got the ice table, we've got our Kb equation, we've got our Kb that we've worked out, and we've plugged in our values into the table. And now continuing those calculations, in case you're wondering where the Kb came from, I looked up the Ka value for HCN, used Ka times Kb equals Kw, rearranged that to get the Kb. Now I'm using the value that I have for Kb, plugging into my equation, solving for x, and what I've solved for, if I look back at my ice table, X is the concentration of hydroxide. How can I use that to get the pH? Well, not directly, but I can use the hydroxide concentration to get the pOH by taking the negative log of the hydroxide concentration. Then I remember that the pH plus the pOH equals 14. So just rearranging that equation, I can solve and plug the numbers, and I end up realizing that I get a pH of 11. So in other words, I get a basic solution. Why do I get a basic solution? Again, my salt consists of a cation and an anion. The cation won't hydrolyze. The anion will hydrolyze. When the anion hydrolyzes, it's a source of hydroxide ions producing a basic solution. Second example, what would be the pH of a 0.200 molar ammonium chloride solution? Well, ammonium chloride, that's a salt, so it's going to dissociate. It forms the cation ammonium and the anion chloride. We know that the chloride ion does not hydrolyze because it's the weak base of a strong acid, so it will not hydrolyze. Ammonium, however, is the conjugate acid of the weak base ammonia, so it is capable of hydrolyzing. The ammonium ion is going to go on to react with water in a hydrolysis reaction to produce ammonia and hydronium. That's our hydrolysis reaction. We're plugging that into the ice table. Again, we started off with 0.2 molar ammonium chloride. So because of the equimolar amounts of ammonium chloride and ammonium, the initial concentration of ammonium is 0.2. Plugging in the rest of my values into the ice table, I get the equilibrium concentrations for all the species. I was given the Kb for ammonia, but I need the Ka since this table clearly shows I have an acid equilibrium. I use the fact that Ka is equal to the Kw over the Kb to work out the Ka for the ammonium ion. It's 5.6 times 10 to the negative 10. Then I come up with my equilibrium expression. It's the product of the product concentrations over the reactant concentration. Plugging in the values and using the 100 rule, I can solve for X. Looking at the ice table, what does X represent here? X represents the hydronium concentration. I can use that directly to get the pH of this solution. At this point, you might want to try some of the questions from your textbook that are listed on the slide. Oh boy, well, what happens when we have a salt that has both acidic and basic possibilities? If we have a cation and an anion that can hydrolyze. And just to make it more fun, we're going to take a cation that can hydrolyze, and our anion is actually what we call an amphiprotic ion, which means it's capable of acting as an acid or as a base. So take a look at the ion, see the two equations underneath it. We've got the ion reacting with water to produce hydroxide ions. Since that's a basic solution, that would be described as a Kb. The Kb we can solve by taking the Kw over Ka1, and that's the value of the Kb. In the second equation, we've got the anion reacting with water to produce hydronium ions. That equilibrium can be described by Ka2, which is found in your tables at the back of your book. The Ka for aluminum, acting as an acid, can be derived from the Ka tables in your textbook. So looking at the three equilibrium constants, we see out of the three values, Ka2 is the largest. So that means that it's going to have the most impact on the water equilibrium. And so this salt is going to produce an acidic solution. There's the qualitative explanation. Let's look at it quantitatively. Find the pH of this 0.1 molar solution of this salt. We're going to use the Ka2 value, so we using that equilibrium. Notice here that when that salt dissociates, we have a 1 to 3 molar ratio. So if I start off with a 0.1 molar salt solution, I end up with 0.3 moles per liter of the anion. So that anion concentration is going to go down by the hydrolysis reaction. The ion values are going to go up. So I've got my Ka. I've already solved for Ka, plugging in my values, and of course the 100 rule is still valid. You can see the work at the left to prove that it's over 100. So I'm going to drop that bottom x out of the equation, solving for x, and again, referring to the table, x is the hydrogen or hydronium ion concentration. So I can use that directly by taking the negative log to get the pH. One last thing, just want to remind you of what you learned in grade 11. When metal oxides react with water, they produce basic solutions. Okay? That's because when metal oxides react with water, they always produce the metal hydroxide. When non-metal oxides react with water, they always produce acidic solutions, and that's because when they react with the water, they're going to form acids. So there you go. There's the explanation. You thought all salts were neutral, but now we've completely changed your thinking.